This is Suvarchala, working as an associate professor, the Department of Computer Science and Engineering at Institute of Aeronautical Engineering. As a part of the Database Management System lecture series, in this lecture, I'd like to discuss about B+tree indexing file organization techniques. In previous sessions, I discussed about the file organization techniques, various techniques of file organization as sequential file organization, hashing, and index file organization techniques, cluster, multi-table clustering, etc. So today first in this session we'll discuss about basic indexing structure and how B+tree is more efficient than basic indexing file organization techniques will be discussed now. Index mechanism is used to speed up the access of the desired data. So that means if the data is organized as per the search key value, then the attributes of the search key will be used to look up the records in the file. An index in a file consists of the two attributes, search key value and the pointer that is addressed to the respective record. Index files are typically much smaller than the original file, and two basic kinds of indices are ordered indices and hash indices, which were already discussed briefly in the previous session. In case of order indices, the search keys are stored in a sorted order, and hash indices means search keys are going to be distributed uniformly across the buckets by using a special function known as hash function. So which type of indexing is more suitable to store our database is based upon some parameters or metrics. Access types supported efficiently records with a specific value in attribute or records with an attribute value falling in a special range of values. So that's why whenever we are evaluating an indexing structure, access type, access time, how much time it will take to insert a record, how much time it will take to delete a record, and management of the free space, that is space overhead. These are the parameters to be considered to decide which indexing organization is best suitable to store our or to represent our data. Ordered indices means in a ordered index structure, index entries are stored in a sorted order on the search key value. For example, author catalog in library or in dictionary, we can say. So, primary indexing means here, in a sequential ordered file, the index whose search key specifies the sequential order of the file, that is called as a primary indexing. This is also known as cluster indexing. Why? Because sometimes these index values are going to be having a group of values, multiple indices. Search key consists of multiple values, multiple indices are available. Then we may call it as a cluster indexing. The search key of primary index is usually same primary index is considered as a search key itself, but not necessarily it is a primary key. So if the data was stored, for example, when we are arranging our data in our table, if any one of the key value attribute is a primary key we defined as a integrity constraint, then automatically our data will be stored according to the primary key order. So that's why whenever we are accessing the data based upon the primary key, searching is more efficient because it is in the order of this primary key only now. So we can use binary search so that efficient search process is representable. That is, the lookup process is more efficient in such cases. And sometimes what happens, the lookup process may need not be on primary key always. Depending upon the need on other attributes also, we have to check the conditions. For example, when we are storing our students' database, we will take generally our hall ticket number of the student or registration number of the student is as a primary key. But always based upon the registration number only, the search process may not be considered. For example, would like to get the students who got a first class or a grade A in previous examinations. That is, searching is on grade. For example, you have to get all students who are under scholarship holders. That is, the attribute is scholarship holders or not. That means the search process is going to be not only based upon the primary key, but maybe based upon the various other keys also, various other attributes also. In such cases, we can use this indices concept so that index file is created based upon the attribute on which frequently search process is carried out actually. So that the searching is going to be more efficient actually. So, secondary index can be considered an index whose search key specifies an order of different from the sequential order of the file. Then we will call it as a secondary index, or we may consider it as a non-clustering index also. And ordered sequential file with the primary index is known as index sequential organization. These indices are categorized into dense index files as well as sparse index files. Dense indexing means, as we discussed earlier, whenever an indices was created on a particular attribute, a separate file is going to be generated known as index file, which consists of two attributes, index key value, that is search key value, and the address of the respective key value record. So in case of dense index file means all attribute values, that is all search key values upon which the indexing was made, all values are available in our index file also, then we will call it as a dense indexing. Now you observe here, if indexing has been made on a ID here, then each ID will be appear in our index file. So this index file, each ID is there means for every ID, respective pointer is pointed. Such kind of indexing is known as dense indexing. So dense index means index record appears for every search key value of the original file. Dense index file is observed here, for example, the instructed, the data, dense index on department name with instructed file sorted on department name. But department name was repeated here. So that's why in such cases, the department name is going to be having here, but multiple, the first record of the cluster is going to be considered. Now you observe biology. Biology is pointed to this record where biology is there, but only one record. Computer science is pointed to the first record of the computer science cluster. And from there onwards, all other records are going to be carried out till there is no computer science while doing the search process actually. Similarly for electrical engineering and finance, history, music, physics, etc. This is also a dense indexing, but each index value is having repeated values, that is cluster values. So that's why those are represented only once in our index files. Sparse index file means it contains index records for only some search key values only. So for example, the previous case only, if ID is there, sparse indices, first index value is there, second 32343 is there. That means up to that the search process is continued. For example, I am searching the value for 1515. First we will search here. So if it is less than 151, yes. And so next record is in index file was searched 32343, it is greater. So this must be in between these two. So I supposed to start in the previous value and I search in a sequential manner. If it occurs, search is successful, otherwise search is unsuccessful. So applicable when the records are sequentially ordered on a search key value. But remember, the records must be ordered in a sequential on a search key. To locate a record with a search key value k, find the index record with the largest search key value which is less than k, then search file sequentially starting at the record to which the index record is pointing. Comparing with the dense indices, Spurs index file takes less time, so maintenance is also less. Overhead of insertion and deletions are also less. But it is generally slower than dense indexing for searching process. Why? Why? Because the group of records are allocated. The group of records are going to be allocated. Those records are processed as a sequential order actually. That means once we identified in which group it occurs, then in that group the sequential process has to be considered. So a slower search process. So that's why Spurs index with an index entry for every block in a file corresponding to least search key values in the block, as well as the process of searching also could be little bit increased. Like that, we have to consider the trade-off between these sparse and dense indexing techniques so that the organization of the data increases our search process efficiency. Secondary indexing means here primary index points to the your secondary index. From there, the pointer is pointing to the original data. So index record points to a bucket that contains pointers to all actual records with that particular search key value. And generally secondary index can be dense indices actually. This kind of indexing file organization has its own advantages and disadvantages are there. And disadvantages of indexed sequential file are performance degrades as file grows. That means if file is keeping on adding the records, what happens? More number of records are added. Index file is also going on increasing. So automatically the performance is going to be decreased. In such cases, what happens? Overflow buckets are to be created by us. Then performance degradation is there. So if on the same search keys, if any growing and shrinking of our database is very, very frequent and in high volumes, in such cases, periodic reorganization of the entire file is needed actually. That means we have to reorganize our indexing process every time. So that is also an expensive process. To avoid these two disadvantages, another indexing structure can be introduced, which is the most popular indexing structure, that is B plus tree indices. These most of the real-time commercial database softwares are also supporting this B plus tree indices, which is an alternative to indexed sequential files for storing our databases actually. So, advantages of this B plus tree index files are it is automatically reorganizes whenever we are doing the process of additions, insertions and deletions of the data records into our file, then automatically the B plus tree indices are going to be reorganized. So automatically it reorganizes itself with small local changes in the phase of insertions and deletions. So there is no separate reorganization process separately. During these type of operations only automatically the reorganization of B plus tree carried out. Reorganization of the entire file is not required to maintain the performance. But some disadvantages are also there. The small disadvantage with the B plus tree are extra insertion and deletion overhead is there and space overhead is also there. We need to add nodes whenever the database is going on increasing. Similarly, sometimes if the deletions are more and the nodes have to be again sent back to our free space. This organization is a little bit overhead will be considered as a disadvantage. And advantages of B plus tree are it is very, very effective in search process and B plus trees are used extensively in real-time applications. So this is one of the examples of B plus tree. B plus tree, you are just observe the records are stored and we will call each of these as a node. So this is known as nodes actually. These nodes are available to us. Each node will have some size. Let us assume that some n is equal to 6 or n is equal to 8 like that. Node size will be there. N is equal to 6 indicates that 6 pointers will be there. 6 pointers means n minus 1 values can be stored. N minus values can be stored. Now you observe here, in this example, our node is having value as a 4. N is equal to 4 means 4 pointers can be stored. This is 1, 2, 3, 4 pointers. 4 pointers means 3 values. This is the root node and these are the internal nodes. This is a leaf node or external node we will call. Let us assume that this is the block of the data stored in our secondary storage device, original data. So when we are organizing our data by using B plus means here, and you observe here, the first one name starts with M. This less than M will be pointing to this tree and greater than M here pointing by this tree. This is same as our binary search trees used for storing our data in a, for example, each node have left child as a less than the values, right child as will have the greater than or equal to values. Similarly, binary, ternary or n-way trees are there, no? Similar to that only here. Here B stands for balance. So that means here the tree will be in the balance. Balancing means here from root to leaf node, the length of the path will be the same for any leaf node. Now you observe here, internal nodes and root node will give a path to reach the search key values. But leaf node will give the search key value and actual address of that particular key also. Now you observe this bandit is having a key value, no? So before that its address will be stored, right? So after that you are going to store the respective values. Every value which is pointed, the before pointer, the first pointer of the pointer before this particular attribute points to the actual address of the respective record. You observe here Calipari pointing to this record, Crick pointing to this record. But it is having an additional pointer, no? That pointer points to the next leaf node. Here you observe Einstein pointing this Einstein. Side pointing here. Gold pointing here. And so on and so forth actually. So bandit is pointing to bandit. That means the actual pointers are stored in the leaf nodes and the root and internal nodes are providing a path to reach our search process actually, to reach our needed record. So the B plus tree indexing files is a rooted tree satisfying these following properties. All paths from the root to the leaf are the same length. That's why we are calling them as a balanced. B stands for balanced here in this example. Each node that is not a root or a leaf has number of children between n by 2 and n. That is all internal nodes will have children between n by 2 and n. That is each non-leaf node must be, other than root, must fill minimum 50%. The leaf node will have maybe more than 50% and up to n minus 1 values. A leaf node has between n minus 1 by 2 and n minus 1 values. That is, it can be full also. And root will have minimum 2 children. Then only the tree is going to be possible. If the root is not a leaf node, then it has at least 2 children. And if the root is a leaf node, then it may have children between 0 and n minus 1 values. That is, root itself is there. No children are there means it may store complete n minus 1 values or 0 if no children are there actually. So what is the structure of the node in our B plus tree? A node structure consists of P1, K1, P2, K2, P3, K3 and so on and so forth. An additional point Pn minus 1, Kn minus 1 will be there. Additional pointer Pn will be there. That means here Ki are the search key values, Pi are the pointers. That is the addresses of the children. Pointers to the children in case of non-leaf nodes, and pointers to the original records, bucket of the records if it is a leaf node. So this Pi represents pointers. The pointers may be to its children or the pointers may be to the original records of the secondary storage depending upon its internal node and external node. And remember that search key values must be stored in a sorted order. That is, K1 must be less than or equal to K2, not equal. We are not considering duplicates initially. So K1 less than K2, less than K3, less than K4 and etc. Kn minus 1. So initially we are going to assume no duplicate keys are allowed. Address of the duplicate key process is going to be addressed later. These leaf nodes are going to be having the properties like for I is equal to 1 to n minus 1, pointers Pi points to the file record with the search key Ki. From first pointer to n minus 1 pointers. Right? So Li, Lj are the leaf nodes. Then the last pointer of Li points to the next leaf node, that is Lj. I less than j, Li's are search keys values less than the search key. All search keys will be in a sorted order. The search keys of Li's must be less than search keys of Lj. Within the node also the keys are going to be arranged in sorted order. And Pn pointer points to the next leaf node in general in a sorted order. So for example, you observe here Bandit, just now previously I told you, this is Bandit, California and a creek, Calipari and a creek, and this pointer is pointing to the next leaf node. So this is the structure of the leaf node actually. Structure of the non-leaf node. Non-leaf node also consists of similar, but all search keys in the subtree or to which P1 points are less than K1. This is pointing to a tree which is less than K1, and this is pointing to a tree which is greater than or equal to K1 and less than K2. So that means here the respective process, all search keys in the subtree which points P1 is less than K1, but the remaining things are 2 less than or equal to I, less than or equal to n minus 1. All search keys in the subtree to which Pi points values are greater than the Ki minus 1 and less than Ki. All search keys in the subtree which Pn points to have values greater than Kn minus 1. This additional one is there, no? This is greater than Kn n minus 1. So this is the non-leaf node actually. This is an example of leaf node for n is equal to 6. N is equal to 6 means 5 pointers, as I explained you. 6 pointers will be there, 5 values will be there. So leaf nodes must have between 3 and 5. Why? Because leaf nodes must be having the values n by 2 and n minus 1. So n is 6 now, that's why 3 and 5. Non-leaf nodes are between n by 2 and n. That is 3 to 6 children can be having. Root must have at least 2 children. Now you observe. So EA say less than EA is either first child, first subtree, and greater than the names started with the EI and less than MOR second subtree and more than MOR third subtree. So what are the observations related to the B plus tree are? These are inner node connections are done by the pointers, that is logically closed blocks need not be physically close. All need not store at a single contiguous memory block. We can store the various locations. Each node can be stored at various locations because anyway pointers are there, no? Those are addresses. Non-leaf levels of B plus tree from a hierarchy of Spurs indices. B plus tree contains a relatively small number of levels because the level below root has at least product of the 2 multiplied by n by 2 values. So that's why the depth of the tree is relatively less. Because of that, what happens? The searching process takes very less time. Depth is less, no? So that's why log n by 2, log k to the base n by 2 is the height of the tree now. Height of the tree or depth of the tree. So that the search will also takes almost that much time. Search success can be conducted very effectively and very fastly because log k to the base n by 2. So how to search for a value in a B plus tree? First starts from the root. If root is a not leaf node, then we will process. The process is like that. First we will search. If it is not a leaf node, search process is continued. For which value? K value is less than the given V value. And the respective tree path is going to be pointed. So let I be the least. For example, when you are searching for a value, it will search the process actually. So when we are using the search process here, the I be the least value such that Ki is equal to V. If there is such value, I follow the pointer Pi to the desired record. Once if we reach the leaf node, in that the search process is going to be in a sequential order. Duplicates can also be handled by this B plus tree. That is, in both leaf and internal nodes, duplicates are possible. Instead of using less than, you can use less than or equal to. Guarantee that K1 less than or equal to K2 less than or equal to K3, etc. Search keys in the subtree to which Pi points are, instead of using less than strictly, less than or equal to Ki can be used. But it must be used less than only. Why? Because same search key value is present in two leaf nodes L1, Li and Li plus 1. Then the parent node Ki must be the equal to P. So even duplicates are there in non-leaf node, that is internal nodes, no need to modify. But in the leaf node only, all of them will come under as a same group. Of course, may not be the same leaf node. Maybe next, if Li first value occurs in Li, next duplicate value may occur in the Li plus 1 if it is a last value in the first leaf. So we find the procedure also. Traverse Pi even if V equal to Ki. As soon as we reach the leaf node C, then check if C has only one search key value less than V. If so, set C is the right sibling of the C before checking whether C contains V or not. So to print all them, modify the find procedure to find the first occurrence and traverse through consecutive leaves to find all occurrences of V. That means first value will be searched as usual. Once we reach the first value, from the first value, sequentially search in all leaf nodes till we will get which is not equivalent to the current value. So that all values are going to be processed, or process may be printing or anything. So queries on B plus tree, if there are K search key values are there in the file, the height of the tree will be log k to the base n by 2, and a node is generally same size as the disk block, same as generally 4 kilobytes, etc. So that what happens, the block is going to be transferred to the node actually. In a balanced binary tree, various number of search keys are going to be there. Around 20 nodes are going to be accessed to look up the process actually. So if you would like to do some updations, that is insertion, deletion, those are also possible in our B plus tree. But updating a key value is there. It's not possible in B plus tree. It's not possible in the sense that we cannot as it is updated. What we supposed to do? Updation of a key value means it is a sequence of deletion and insertion process. Okay, modifying key value is not possible. If it is possible, you have to propagate this process of changing the values if the parent occurs with the key value. So that's why generally it is better in insertion and deletion process. If would like to insert, where is supposed to be inserted? First, we have to find out the leaf node in which the search key value would appear. If space is there in the internal node, we will add that particular record to the file and adjust ordering of the record. If necessary, add the pointer to the bucket also. If the search value is not present, then add the record to the main file, a create bucket. If there is a room in the leaf node, insert it with the key value and arrange them in a sorted order. Otherwise, splitting of the node is considered. If the splitting of node is resulting to split in the next level also, next higher level, that is parent level, it has to be done. This process is continuously propagated towards upward direction depending upon the necessity till the root edge. What is meant by splitting of the node? For example, there is no space in the current node anyway, then the node is going to be split into two nodes. Splitting means a new node is added as a neighbor to that particular current node. So new node added means here 50% of the, because it is already full node, so the first 50% of the values will be in the old node itself. The next 50% of the values are moved to the new node created. According to that, the parent has to be modified. If the while modifying the parent also, that is in the parent also, a new pointer is going to be pointed. If space is available, it's okay. If the space is not available, again splitting is going to be considered. So for example, you observe here. So in the previous, we are having items. We have a node which is having the queries, bandit and Calipari and Crick. It is already full. So we would like to add a new value as Adams. If I would like to add Adams, it must be added before bandit. No space. If I would like to move these 3 means 3 only the node value, no, so I cannot move. Then I am splitting. So while I am splitting, if it is a leaf node splitting, Adams and bandit will be there in the first node and Calipari Crick will be in the second. And there will be a pointer to this one, and this is pointed to the next node of this original before splitting original node. The result of splitting node contains bandit and Calipari Crick inserting Adam and insert entry with parent also. So what is splitting of the node? Take n pairs and in original node, and whatever n by 2 values will be in the original node itself, and the remaining n by 2 values will be in the new node. Let the new node be P and K is the least key value of the P. Insert KP in the parent of the node being split. Again, insertion of the parent results or requires splitting. Parent is full in other sense. Again, split the parent also, propagate same to the upward direction. So, for example, you observe here, as we discussed here, the Adam was inserted and this was modified. And here Calipari was supposed to be inserted here. Previously it is instant, no place is there. It was. This is before insertion, this is after insertion. So before insertion, Einstein gold are there in the next parent level. Calipari was introduced. So that's why it is no need to split further in parent. Space is sufficient currently. So B tree is going to be inserted like this. So whenever insertion is there, internally a copy is going to be maintained separately. Then the respective pointers are going to be modified. So splitting of the non-leaf node, leaf node is splitting and pointing to the immediate one. Non-leaf node means here end-to-end memory area which spaces n+1 pointers n key and copy them back to them. The remaining things are copied to the next node actually. B plus tree is similarly deletion is also possible. For example, before deletion Srinivasan here. So Srinivasan here we are in the original place. Srinivasan is here and in the leaf node Srinivasan is here. Deletion means if I am deleting this Srinivasan here, then what happens here? Only it consists of W. View. So this deletion of view and it can be added here 50%, less than 50% filled, no? So it can be moved here and so that respective header is going to be changed. So to which it was added, the respective key value is added here. So deletion may sometimes, it may be a simple, various cases will be there. Just deletion doesn't reflect our current structure of the B tree. Sometimes because of deletion, entire node will be empty or less than 50% was be filled. In such case, the deleted node must be sent back to our free space actually. So deletion of Srinivasan causes merging of the underfull leaves. Here we merged these two. Because of this merging, then automatically the parent address has to be modifiable depending upon the merge process actually. As insertion leads to splitting, deletion may leads to merging also. So deletion of sing and view from result of previous example, then automatically it will further merging is required. So search key values in the parent changes as the leaf nodes are going to be merged actually. So when we are using this deletion process, before and after deletion of gold from the earlier example. So where is gold? In the root itself. So while doing this, gold is here actually. While deleting here, it is less than n/2. These two can be merged. Right? So these two are merging means here. When we are doing this merge process, then we are going back here. The respective gold has to be changed here. Because of this, these two can be merged. Only single child came. Then the merge process is going to be moved, propagated to the upward direction. Node with gold and curd become underfull and was merged with its siblings. Parent node becomes underfull and is merged with its sibling, and so on and so forth. The value separating two nodes is pulled down when merging process is carried out. Root node then has only one child, so that's why it is deleted. Because root should have minimum 2 children, no? That's why. So find the record to be deleted and remove it from the main file and from the bucket also. And also removed from the leaf node and merge the siblings if those are having the minimum required number of values, that is n/2. And this merging is going to be propagated upward direction depending upon the required processing actually. Whenever we are doing updates on B plus tree, we are going to use this redistribution of the pointers are going to be considered when sibling do not fit into the single node actually. The node deletions may cascade. This is called as a upward direction. We are keeping on merging now. So that's why one node deletion may cascade upwards till the node which has n by 2 or more pointers are found. If the root has only one pointer after deletion, it is deleted and the sole child becomes the root also. So whenever we are processing these, various alternatives are there to uh, non-unique search keys can be considered. So non-unique search keys means the search key is having the duplicates. Various alternatives to scheme described earlier, buckets on separate block, because every time separate block is going to be considered, but it is not good idea here. List of tuples pointers with each key. For this we need some extra code or logic has to be written to handle our long list. Deletion of a tuple can be expensive if there are many duplicates on search key. Which has to be deleted? We don't. All have to be deleted, then it takes more time. And make search key unique by adding a record identifier so that what happens, deletion process will be easy to us. So when we'd like to deleting multiple values may result which has to be deleted or multiple deletions. So when is any process is there, add our record pointer also as a combination of our search key, then it will become unique. So that what happens, the extra storage overhead may be there, but simpler code for insertion and deletions. This is widely used in most of the real-time softwares actually. This B plus tree file organization is a indexed file only, but index file degradation problem is solved by using B plus tree indices. Just now we observed we need not reorganize. Whenever insertion deletions are happening, automatically the organization itself automatically manages it. The leaf node in B plus tree file organization stores the record instead of pointers, and the leaf nodes are still required to be half full. Since the records are larger than the pointers, the maximum number of the records that can store in a leaf node is less than the number of pointers on a non-leaf node. Actually. Insertion deletions are handled in the same way as insertion deletions are handled in the B plus tree indexing structure. So B plus tree is good space utilization, important since record use more space than the pointers. We may be thinking more number of pointers we are using, it may be taking more space. No problem. Instead of storing the entire values, only search key values and the pointers we are storing now. So that's why the space utilization is going to be considered as effective only. But even then we can improve the space utilization involving more sibling nodes redistribution during the splitting and merging. That is, two siblings in redistribution to avoid the split and merge very frequently. So we can introduce two siblings results in each node having at least 2n by 3 entries instead of n by 2. So that the space issues can be solved by us. And record relocation and secondary indices are some of the issues related to other indexing. The record moves, all secondary indices that store record pointers have to be updated. But nodes splits in B plus tree file organization becomes very expensive in such cases. So then what we supposed to do? We can use the primary index search key instead of the record pointer in the secondary indices. That means if the record pointer is used, what happens if the record is moving from one place to other place or secondary indices, then problem occurs. To avoid that, primary index search key instead of record pointer in a secondary index. That means along with the search key, Anyway, that respective table will have the primary key, no, that can be considered, which will have unique values only anyway. So extra traversal of primary indexing to locate the record is one of the additional overhead is needed. Higher cost for queries, but node splits are going to be cheaper. So record ID is added if the primary index search key is not a unique key. So that's why these B plus tree indices are more effective and more easy to manage things most of the time. By using various variations, this B plus tree index organization was used or introduced in most of the real-time database management commercial softwares also, so that the effective search process is carried out actually. So thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.